All right, folks, let's go ahead and get started with the second half of class. I did see that there were a few questions in the chat, and I think those are super important conceptual questions. So let's maybe attack those before we talk about some more of the indeterminate forms, okay? So I'm going to include this in the bottom of the 10.2 notes, just because that's what I have open right now. And actually, maybe I'll just stick it at the top. Okay. All right, so I'm gonna go ahead and share my screen, and then hopefully we won't encounter too much of this lag that I was feeling the first half of class. Okay, so I'll kind of put this in this little corner over here, but when we're doing this, keep in mind that we're finding limits, not the exact value that happens at that point. And so when we're finding a limit, it just means what we're getting really close to, not what the actual value is. So for example, if I think back to the previous one, and actually I think I have room on the other document. Okay, let's put it here instead. I'll put in the 10.1. So if I have a situation where I have, let's go back to this. The limit as x approaches infinity, and we had 2 over the square root of x, right? And so we ended up with 2 over infinity. But what we're doing here is not necessarily finding the exact value, like what is 2 divided by infinity, because that is undefined. But what we're doing is finding the limit, meaning we want to see what happens, what y value comes out when x gets really, really close to infinity. So you could even think about this like 2 over, like, let's put in 100,000. All right, that number is getting really close to it gets close to 0. It doesn't ever actually get to 0. Like if I did 2 over 1 million, does that get closer to a y value of 0? You know, if you do that on your calculator, you should get a number that's even closer to 0. And if you keep going, like you keep putting in larger and larger values of x, or of x, like 2 over 1 billion, you're going to get even closer to 0. So keep in mind here that the defining feature of these problems is we're finding limits, we're not finding exact y values. So if I say 2 divided by infinity just by itself, no limits, that means that it's going to be undefined. Whereas if I say find the limit as x approaches infinity, then you can say the answer is going to be 0 because it's going to get close to 0. Yeah, exactly. We're looking at long-term behavior, or another word for that is we're looking at end behavior here. What happens at the ends, right? And if we graph this, the graph is going to get really close to the x-axis, but it won't ever touch the x-axis. Okay. So folks who were asking about the 2 divided by infinity, does that clarify why we're getting 0, or why we're getting 0?
I think so. So if the limit is a value over 0, you're going to be approaching infinity. If the limit is a value over infinity, then you're going to be approaching 0.
Yeah.
It's just going to be pretty much the opposites.
Mm-hmm.
Okay.
Yeah. So I think the example that I use is like, let's say I bake a cake, and if I have one cake and I want to share it with not that many people, then people get a lot of cake. Whereas if I bake one cake and I share it with like the entire Mesa campus, everyone's going to get like a crumb. Right? Like when we're dividing things, that's what we're talking about. It's like how big is each piece if we cut it into that many pieces? Yep. So if I have one cake and I want to share it with no one really, then there's sort of an infinite amount of cake. Whereas if I have one cake and I want to share it with a lot of people, everyone is going to get a really, really small piece, or basically people are going to get no cake.
Very, very quickly, might be kind of a dumb question, but indeterminate and undefined, are they like, is there a big difference between those two? Because we're looking at indeterminate forms, but a number over 0 is usually undefined. So is there like a big difference between those two? Or are they like the same thing?
I don't think anyone uses the phrase undefined form.
Okay.
But conceptually, yeah, that's basically, you're getting to a situation where you're like, if I put this into the calculator, I'm going to get an error. That's basically what the indeterminate forms are.
Okay.
Okay, cool. All right, so we spent the first half of class talking about one particular indeterminate form, which is the 0 over 0 or infinity over infinity. So in this section, 10.2, we're going to take a look at 3 other indeterminate forms. Okay, so the first form that we're going to look at is a situation where instead of dividing 2 functions, we actually see a multiplication of 2 functions. Okay, so f of x times g of x. So when you look at the problem and you plug in the number, what happens is you get a situation where you have 0 times infinity, okay? And so here's our strategy. If we can change this form of 0 times infinity to a situation where we can use L'Hopital's, then we can solve the problem. Okay, so a lot of these strategies involve a little bit of algebraic work so that we can get it into a form where we can use L'Hopital's, all right? Because taking derivatives of each piece, like the numerator and the denominator separately, that's something that we can all do. And so our job is to try and get it into that format so that we can use that strategy, okay? So here's how we do it. We find our 2 functions and we rewrite them in one of 2 ways. So one way is we could keep the f of x in the numerator, and then we could multiply, instead of multiplying by g, we say let's divide by the reciprocal, which is the same thing as saying multiply by g. But sometimes in this form, it creates a situation where we can use L'Hopital's and then we're good to go. Similarly, sometimes it's better if we take the g of x and we keep it in the numerator, and instead we change the f of x to be 1 over f of x in the bottom. Okay? Now, so applications of this topic, not a ton in terms of like real world applications. Some of Calc 2 is definitely going to be very theoretical. I would say this is more along that theoretical vein, okay? All right, so one question that I often get from students and that I think a lot of you might be wondering is like, how do I know which one? How do I know which one do I put on top and which one do I put on bottom, okay? And so what we're going to do in this first example is we're actually going to set it up both ways. And then we're going to see which one seems easier to us, and we're going to do that way. Okay? So we're thinking about, we could do either method, but usually one of them is going to be easier than the other. So with example 1, let's call our f of x is going to be this first one, okay? So f of x will be the x squared. That means that's going to stay in the numerator. And my g of x then is going to be the natural log of x, and that's going to be, we're going to write that as 1 over natural log x. Okay, so that's going to be our setup for the first method. For the second method, we're going to keep the natural log on the top, and we're going to write 1 over x squared in the denominator. And we're going to make sure that we keep that limit notation in the front, all right? So we've got the limit as x approaches 0 plus. What does that little plus sign mean, by the way?
You're approaching
Right.
from the right.
Yeah, we're approaching that value from the right, exactly. And so we would write this as x squared over 1 over natural log. Okay. Now, if I plug in 0 over here, I'm going to get 0 over 1 over infinity is going to be 0. Okay, so I've gotten it to a form where, in theory, I could use L'Hopital. Now, let's take a look at that numerator, x squared. Can you guys take the derivative of x squared? And the answer is yes, right? Because even on a bad day, derivative of x squared is like, oh, thank goodness it's so straightforward, just 2x. But what about the derivative of 1 over natural log of x? Is that a straightforward derivative to take? And that answer should be not necessarily, okay? It's not, you can't just do the derivative of natural log and then take the reciprocal. You would have to use the quotient rule here. So this bottom part is not that easy to take the derivative. You can do it, it's just not that easy. You would need quotient rule, or product. You could get away with product as well. And you would also need chain rule, right? So that's just something that, if my goal is to make this problem easier, that's not necessarily taking me in that direction, okay? So let's see what happens if we set it up the other way. We keep the pink function on top, and we keep the green function on the bottom. Okay. And I double check, can I use L'Hopital's here? And I end up with negative infinity over infinity. And so yes, this is a case where I could use L'Hopital's. So derivative of the numerator. What do we get for the derivative of the numerator?
One over x.
1 over x.
1 over x. Now, how do I have to, what rule do I need to take the derivative of the bottom?
Power rule.
I need power rule, but I need to think about this as like 1 over x squared is really x to the negative 2. And then that's what I use to take the power rule. So it's going to be negative 2x to the negative 3, okay? And if I rewrite that as a fraction, I end up with 1 over x over negative 2 over x cubed, okay? Now, this seems like a good situation where we saw in 10.1, where we simplify algebraically and then see if we can plug in our number again. And so when we do that, we're going to end up with x cubed over negative 2x, or negative x squared over 2. And now if we plug in 0, we're going to get 0 over 2, or we get a final answer of 0. All right, there it is. Sorry about that. Okay, so in terms of the decision making, at least in the beginning, especially for the quizzes, I would try and set them up both ways. You don't have to do them both ways, but by setting it up, I think it'll be good practice in that decision making, which way comes up with derivatives that are easier to do. And in this case, you could certainly try the first way, but the second way I think is a little bit easier because we have one that's just a straight up rule, the other one is just the power rule, okay? All right, so let's take a look at example 2. And what I'd like you folks to do is to set up the derivatives, or set up for both ways. So if you change this to be f of x over 1 over g of x versus g of x over 1 over f of x, and then see if you can tell which one might be easier to take the derivative of, okay? Okay. So before we talk about the rewriting, one thing I really want to emphasize, so I'm sorry I forgot that, is we want to always try plugging in the number first, right? And seeing which indeterminate form it is. And when I do that, I end up with a 0 times infinity, okay? And so that 0 times infinity tells me, all right, I should try and rewrite this in a way that I can use L'Hopital's. And so that involves some sort of reciprocal, either the reciprocal of the top or the reciprocal of the bottom, to create a fraction so that I can use L'Hopital, okay? So of these two setups, which one do folks think might be a little bit more straightforward when it comes to taking derivatives?
The first one?
The first one, what makes you say that? I would agree with you, by the way.
Because the derivative of secant's a lot easier.
Ah, okay. But we don't want the derivative of secant. We want the derivative of 1 over secant.
Loci.
Ah, okay, great. I saw that in the chat window as well. It might be really helpful for us to write this, keeping the 2x minus pi, but instead of 1 over secant, that is the same thing as cosine x. Like 1 over secant is the same as cosine. And so now if we use your line of reasoning, the derivative of cosine is super easy. But what makes the second one hard to find the derivative? Like, is it the top? Is it the bottom? What's more problematic in that second one?
The bottom.
Yeah, I think for this bottom, just like the last one, we're going to need either quotient or product rule. And we're going to need chain rule. And I can do all of those, and it's not that bad, but why would I do that if the other way is a lot easier? Okay, so once I kind of set them both up, then I'm like, all right, that first one is easier, let's do the first way. So if we plug in pi over 2 into what we have, we end up with a 0 over 0 case. So that means we can use L'Hopital's. And so that means we're going to take the derivative of the top, which is just going to be 2, and the derivative of the bottom, which is negative sine. And when we plug in pi over 2 at this point, we'll end up with 2 over negative 1 or negative 2 as our answer. Okay? So if we look at this graph of 2x minus pi times secant, and we see what happens when x gets really close to pi over 2 from the left, the y value should get really close to negative 2. Okay? So this is our first variation where we end up using L'Hopital's again, but it is considered its own indeterminate form. Okay, so when we have the 0 times infinity, this is the kind of strategy we want to use. All right. Any questions about this strategy? Okay, so let's move on to the other strategy. Okay, so all right. So sometimes you have a situation where you have not a function divided by a function, not a function times a function, but instead you have a function raised to the power of another function. So in this case, we have f of x, and it is being raised to the power of g of x. And so here are some situations that might get sticky for us. We might end up with 0 to the 0, 1 to the infinity, or infinity to the 0. And all of those indeterminate forms means that we're going to try these next 4 steps that we see here. All right. So if we take a look at example number 3, okay, let's identify our f of x, which is going to be this 1 plus 3x. And then our g of x is 1 over 2x, right? So before we do anything, let's confirm that this is indeed one of the indeterminate forms above, 0 to the 0, 1 to the infinity, or infinity to the 0. And so when we plug in 0, we'll end up with 1 plus 0 to the 1 over 0, or 1 to the infinity. Okay? So we know now that we can use these 4 steps to help us find out what y value this function actually gets close to. Okay. So I'm going to write out the whole function. And then we are going to take the natural log of both sides, okay? So let's say that I have y equals the limit of x approaching 0 from the right of 1 plus 3x to the 1 over 2x. Okay, so that's my step 1. Let y equal that function. Step 2 is I'm going to take the natural log of both sides. So natural log of y equals the natural log, or the limit as x approaches 0, of the natural log of 1 plus 3x to the 1 over 2x. Okay, so I've natural logged both sides. So natural log, and that comes out here and here. Now, one of the log properties that you learned way back in the day is that when you have a power, so a function to a power that is being natural logged, you can bring that power down as a coefficient. And so we use that property to generate g of x times the natural log of f of x. And so what that's going to give us is we'll keep the left-hand side the same. The right-hand side is going to become 1 over 2x times the natural log of 1 plus 3x. Okay. The other way we could write this is natural log of 1 plus 3x over 2x. And check out what happens when I plug in 0. On the top, I'm going to get 0, and on the bottom, I'm going to get 0. So essentially, this strategy is just different algebraic steps to get a function into a form where we can use L'Hopital. Okay? So let's keep that natural log y on the other side, all right? I'm a big fan of writing that natural log the whole time, and I'll show you why when we get to the end, all right? Derivative of the bottom just becomes 2. Derivative of the top is not this. Why is it not that? And what should it be instead?
By 3.
Yeah, why is it times 3?
Chain rule.
Yeah, we need to use chain rule here, okay? So this 1 plus 3x, we also need to multiply by the derivative of that function. That's going to change the numerator to be 3. And so now let's try plugging in the zeros again. I get 3 over 1 over 2. Or I get natural log of y equals 3 halves. So here's the deal. I'm writing this natural log of y the entire time because at the end of the day, I want to find y, not natural log of y. And if you don't write out that part, what I've seen a lot of students do is they get to the end and they're like, I got a number, great, I'm going to stop right here and that's my answer. And that's kind of like in those trig subs where if you end with theta, you're not quite done because you didn't get it back into the form with x's, all right? So we're not going to put a box around that 3 halves because we have one last step to get y by itself, and that is to raise both sides e to the power of both sides. And so on the left, that will give us y. And on the right, that'll give us e to the 3 halves. And not 3 halves, but e to the 3 halves is our final answer. Okay. So a different format, and the question really is, how do we get that thing out of the exponent? And that's where logs tend to come in handy. Okay. So what I'd like you folks to try is I'm going to give you about a minute or two to get a head start on question number 4. Okay. And let's start with that one, and then I'll catch up to you with the work, and we'll kind of check along the way and make sure that we're doing all the right steps for this kind of question. Okay, so with example 4, I started by plugging in my number, right? I'm plugging in infinity, see what I get, and I get a 1 to the infinity. And so I know that that is a case where I want to use the idea of a natural log so that I can get one of the functions out of the exponent and then be able to find the limit. So I started off by writing this as y equals that limit, and then taking the natural log of both sides, right? What happens next? That power is going to come down to the front. Okay. Now, if I plug in infinity right here, I get infinity times natural log of 1 is 0. So I actually end up with the other indeterminate form that I found. And what was our strategy when we have two functions multiplied by each other and we wanted to find that limit? Well, we had to write one of them as the reciprocal, right? So which function is going to be easier to write as the reciprocal here? The x or the natural log of 1 plus 1 over x?
The x.
Yeah, I think the x, right? Because we got to take the derivative of both functions. So I don't really want to make the natural log one into something where I need quotient and chain rule. So instead, I'm going to move the x into a 1 over x in the denominator. From here, we're going to go ahead and take our derivatives, okay? So natural log of y equals the limit as x approaches infinity. I'm going to cheat. I'm going to start with the bottom. The derivative of 1 over x is negative 1 over x squared. Okay, so we're just using the power rule here. So we're gonna have to add a power, and that power is -1, so that's why it becomes, or lose a power rather, so it's gonna be -1 minus 1, which gives you that -2. Now, when I take the derivative of the natural log, I'm gonna need to use chain rule. So I have the 1 over 1 plus 1 over x. That's 1 over the inner function. And now I need the derivative of 1 plus 1 over x. And that derivative is going to be -1 over x squared. Okay, so this is the chain rule. Now, without much rewriting, I can see that I can cancel this and this. So that simplifies things quite a bit. So we get the natural log of y equals the limit as x approaches infinity of 1 over 1 plus 1 over x. So let's plug in our infinity and see what we need to do. If I plug in infinity, I'm going to get 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0, which is 1 over 1, which is 1. So really, we have natural log of y equals 1. But we don't want to box off that answer. We want to make sure we raise both sides, like e to the power of both sides. So we end up with a final answer of y equals e. Okay. Now, you might have seen this at some point in your mathematical career, because this is the definition of where e comes from. We take this limit of 1 plus 1 over x to the x power. Okay. So, questions?
Why does the 1 over x on the bottom turn into -1 over x squared?
Okay, so the derivative.
Oh, it's just the derivative.
1 over x.
My bad.
Yeah.
Cool. Thanks.
I know, I feel like the transition is a little rough between chapter 9 and 10 because 9 is like all about integrals, right? And we've gotten so fluent with our integrals. We've done some really advanced work, and now we're like, oops, so remember those derivatives? Now we got to go the other way again. Okay, and so that's kind of like just something that we need to get used to, is like, are we taking derivatives or are we taking integrals? And always thinking about a lot of the rules that you're going to see are not going to be as complex as what you learned in Calc 1, but it's just that you need to recognize that they're there. Okay. All right. So folks, we have one last type of indeterminate form, right? And that is this. Sometimes we end up with a situation where you have one function and you're not adding, you're not multiplying, you're not dividing, you're not raising it to a power, but you're looking at that difference between the two. And so what we're going to do here is think about these strategies. So again, a lot of these questions are going to be in fraction form already. And so if we kind of look at example 5, I'm like, well, if these were in a single fraction, then I could use L'Hopital's, but they're in separate fractions. And so what we're going to do is we're going to combine two fractions into a single fraction. That's going to be our strategy. Okay, so no natural logs, no reciprocals, but in the case where we have a difference, we want to combine those two into a single fraction. So let's take a look at this first example. And what happens when we plug in 0? I end up with 1 over 0 minus 1 over 0, which is infinity minus infinity. And so that matches exactly with the case that we have here. So then we're thinking, all right, let's take two fractions, turn them into a single fraction. And when we're doing that, we want to think least common denominator, right? So with this first fraction, what do I want to multiply by to get it to have a common denominator with the second fraction?
X.
Yeah, and so we're going to multiply it by x over x, okay? Minus the 1 over x, I'm going to multiply that by e to the x minus 1 over e to the x minus 1. And so from here, let's combine and see what we get. I have the x on the top and minus e to the x. But what's the last term in the numerator?
+1.
Ah, why is it +1?
You distribute that negative.
Yeah, this negative sign, you have to distribute it to the e to the x and that minus 1. So that's why we end up with a +1 on the end, okay? Those little fine mistakes, you've seen me make them a lot. I want to make sure those are ones that we try really hard not to make, okay? So let's go ahead and plug in 0 and see what happens. So I end up with 0 minus 1 plus 1 over 0 times 1 minus 1, which is 0 over 0. So by combining these into a single fraction, we were able to get it into a form where we can use L'Hopital's. All right, so let's apply L'Hopital's. The numerator, let's see, derivative of x is 1 minus derivative of e to the x is e to the x, and the derivative of 1 is 0, so I don't have to write it. How do I find the derivative of the denominator?
Product.
Yeah, I'm gonna need my product rule here, okay? And because it's been a while since we've seen product rule, let's go ahead and do it off to the side. All right, so product rule says you have one function and you have the derivative, and you have another function and you have that derivative. And so what we need to do here is plug these into the formula, u dv plus v du. And so that'll give us x e to the x plus e to the x minus 1 times 1, okay? And once we've done that, let's plug in 0 again and see what we get. So on the top, we get 1 minus 1 over 0 plus 1 minus 1. So we still have the indeterminate form. That means L'Hopital's one more time. So this numerator becomes negative e to the x over. To find the derivative of x e to the x, I got to use that product rule again, okay? So u equals x, du equals 1, v equals e to the x, dv equals e to the x, and that will give me u dv minus v du, okay, plus the integral of e to, or the derivative of e to the x is e to the x, and then that 1 goes away. Sorry, this should be a minus plus. Okay. Now let's plug in 0 again and see what happens. I get -1 on the top, 0 plus 1 plus 1. So I get a total of -1. Okay. Any questions about number 5?
So whenever you see the sum and difference of functions, your first instinct that you want to do is combine it into one fraction.
Yeah, exactly. All right. So knowing that, let's do number 6. Okay, so same thing, I'll give you a couple minutes to get started on that, find that common denominator, make sure that you need to use the rules, like is it an indeterminate form or do you actually get a number in the beginning? And then we'll work through that and see what we get, okay?
Would you mind scrolling up just for 1 second to example 5?
Oh, yeah. How's that? Whoop, how's
Cool.
that? Okay.
Yeah, that's fine.
Okay.
I just wanted to make sure I got the right thing down.
Yeah.
All right, sweet. Thank you.
Mm-hmm. All right. So first thing I did was plug 1 into the original function, right? Before we do all this work, let's make sure we need to do all this work. And indeed we do, because we end up with an infinity minus infinity situation, okay? So that means we're going to try and find a common denominator and write these two fractions as a single fraction. Okay, So I found my common denominator, and the very first thing I did was see if I could just plug in my number now, okay? And it turns out that I end up with a situation where I can use L'Hopital's. So that means that I'm gonna have to go ahead and find my derivatives. So the numerator looks pretty straightforward, but that denominator, we're gonna need product rule, all right? So the numerator, I get 1 minus 1 over x. And in the denominator, right, let's do that work off to the side. U equals natural log x, du, v is x minus 1, and dv is 1. So u dv plus v du. And let's clean that up. And we get natural log x plus 1 minus 1 over x. And so we pause here, we try plugging in our number again, see if we can stop right here. So 1 minus 1 over 0 plus 1 minus 1. And nope, we got to do L'Hopital's one more time, okay? So the numerator, I have to use the power rule. So I'm going to get a 1 over x squared. The natural log turns into 1 over x. The 1 turns into 0. And then again, I have a plus 1 over x squared. Okay. Do not do this next step. Why can't you do that?
The bottom's connected by addition.
That bottom's connected by addition, okay? So sometimes we fixate so much on like what's getting canceled that it's like, well, I just see the same thing on the top and bottom, so I can cancel it, but we need to make sure that's like everything is multiplied, okay? So I'm gonna undo that. We don't wanna do that. But again, as soon as I have my derivative, then I should try plugging in the number again, okay? So let's plug in 1 this time and see what we get. And I got a number. And so that means that 1/2 is the y value that this function gets close to when x gets close to 1 from the right-hand side, okay? All right, so folks, that is it for 10.2, all right? So today's quiz, the one that is due tomorrow, should cover 10.1 as well as 10.2. And I believe on every quiz document, I tell you like what sections it's gonna cover, so you can kind of see in the, read the top part, and it should say like what sections are gonna be covered in that quiz, okay? But you'll have questions with all the different indeterminate forms, and I think it should be a good chance to practice that decision making. How do I know which one to use? Might need more than one strategy per question, and practicing the actual procedure, okay? Is it okay if I stop sharing the screen, or is anybody still copying down the notes? All right, so I'm gonna stop the share. All right, folks, so that's it for today's class. I know it's been a probably very exhausting last 24 to 36 hours for you folks. So get out of here a couple minutes early. If you have any questions, you're welcome to stick around. Otherwise, I will see you folks on Monday where we finish up chapter 10.
Thank you.